Isn't it kind of wild? We've figured out so much physics, but there's still this huge unknown territory out there beyond what we can currently grasp.
It really is. Like we're just seeing the edge of a giant ocean.
Yeah, exactly. We see the waves near shore, but what's happening way out in the deep, that's what we're diving into today.
hmm We're looking at how physicists make sure our current theories, the low energy ones we use every day, actually line up with whatever's going on at much higher energies, the stuff we haven't explored yet.
It's like trying to understand a whole building just by looking at the ground floor pipes, right?
That's a good way to put it.
And one of you sent us a great source for this, a talk called Positivity Bounds and Effective Field Theories. That's our map for today.
A fantastic source.
We'll be digging into effective field theories, concepts like unitarity, causality, and these things called positivity bounds.
Key tools for navigating the unknown.
It's all about how we make predictions when we don't have the final rule book.
Okay.
Okay, so let's jump in. What exactly are these positivity bounds?
Okay, so positivity bounds are essentially constraints, rules, you could say,
Constraints on what?
on how particles interact. Specifically on the math describing those interactions, the scattering amplitudes in quantum field theory.
Right.
And the really cool thing is these aren't just made-up math rules. They come from really basic principles we think have to be true everywhere. Unitarity and causality.
Oh, okay.
Um,
Unitarity, that's probabilities adding up to one, right? Everything has to go somewhere.
Exactly. No disappearing probabilities. And causality is just, well, cause before effect. Nothing faster than light. The basics.
Got it. So the bounds are like cosmic rule checkers for our theories. Use this analogy I liked. Shadows on a wall. How does that fit in?
Ah, yes, the shadow analogy. Think of our current physics, our low-energy theories, as shadows projected onto a wall.
Okay.
Positivity bounds ensure those shadows could actually come from a real physical object, that unseen high-energy theory.
So the shadow's properties have to make sense. They can't be completely random.
Precisely. They guarantee the shadow is consistent with some kind of sensible source, not just impossible shapes appearing out of nowhere.
That makes sense. Because, yeah, the source material is pretty clear that our knowledge just hits a wall at super high energies.
It does. We expect our current theories, like the Standard Model and general relativity, to break down eventually, maybe at the Planck scale for gravity.
They mention things like strings or totally new frameworks. It's humbling, really.
It is. We don't know for sure what's up there, which leads to the big question. If we don't know the ultimate theory, how can we trust our current ones at all?
And that's where looking closely at how particles scatter at lower energies comes in. Studying the ripples to guess what's deeper.
Exactly that. We analyze the interactions we can see, the scattering events in our experiments.
And that gives us clues.
It does. We use something called the S matrix. It's basically a big catalog of all possible scattering outcomes. By studying it, we can constrain what that high-energy completion could possibly be, even without seeing it directly.
Okay, so we're studying these interactions, and the talk kept mentioning positivity. That's not just a feeling, is it? It's technical here.
Oh, very technical. Yes. Positivity here means that when particles scatter, all the different things contributing to how likely that scattering is the known stuff, the unknown high-energy stuff, all of it has to add positively to the final calculation.
Add positively. Why is that so important? Like, what happens if something adds negatively?
Well, that's where unitarity comes back in. If you had negative contributions, you could end up calculating negative probabilities for something happening.
Which is nonsense. You can't have a negative 10% chance of something.
Exactly. It's physically meaningless. So positivity is a fundamental check. If your low energy theory predicts negative contributions to scattering, it violates unitarity. It just cannot be consistently connected to a real physical high energy theory. It's a dead end.
Right. Unphysical is bad.
Okay.
The talk also spent time on effective field theories, EFTs. Can you break that down simply?
Sure. EFTs are basically our best working models of reality right now, but models that we know have limits.
Like the Standard Model?
Yeah.
And general relativity.
Perfect examples. The Standard Model describes particles and forces brilliantly, except gravity, up to the energies we can test. General relativity handles gravity beautifully, but we expect it to break down near the Planck scale.
So they work great within their boundaries.
Precisely. Beyond those boundaries, we expect new physics. Maybe weird stuff happens inside black holes. Maybe particles are actually tiny strings. Maybe there are totally new forces.
It's like our maps are detailed for the known world, but have blank spots for uncharted territory.
That's it. Physics seems layered, Different rules dominate at different energy scales.
Okay, that helps. Now, the talk zoomed in on massive gravity. What's the story there, and how do positivity bounds fit in?
Right, massive gravity. That's the idea that the particle carrying gravity, might actually have a tiny bit of mass. Standard general relativity says it's massless. For ages, trying to make a consistent theory of massive gravity was, well, a nightmare. The theories kept predicting crazy, unphysical things at high energies. Serious roadblocks.
So people kind of gave up on it for a while.
It looked pretty grim, theoretically speaking. But then the talk mentions this 2016 paper, a breakthrough by Chang and Raman.
What did they find?
They found specific versions, specific parameter choices for massive gravity theories that do satisfy the positivity bounds.
Whoa, so it wasn't completely impossible. The talk called it a tiny habitable island in a vast ocean of impossibility.
I love that. It's a great analogy. It meant maybe, just maybe, a consistent high-energy version could exist.
But there was a catch, right? Something about coupling.
Yes, a crucial catch. While these specific theories satisfy the bounds, suggesting they could be embedded in a high-energy theory, that embedding probably isn't weakly coupled.
Weakly coupled, strongly coupled. What does the difference mean here?
Basically, weakly coupled means particles interact gently. We have good math tools, approximations to calculate things. Strongly coupled means interactions are really intense, really complicated. Our usual tools often break down.
Okay.
So for massive gravity, even on that habitable island, if you assume the high energy theory is nice and weakly coupled, you still violate positivity bounds.
Huh. So if massive gravity is real,
It suggests the underlying high energy theory is probably strongly coupled, or maybe something completely different from our usual particle theories. It makes figuring out its high energy nature much, much harder.
wow. So the bounds don't just say maybe. They hint at the kind of maybe. Okay, then the talk switched gears to SMEFT. What's SMEFT?
SMEFT. That's the standard model effective field theory. It's a more modern strategy. Instead of guessing specific new theories like supersymmetry or string theory, SMFT tries to be more systematic. It aims to list all possible ways new high-energy physics could show up as tiny changes to the standard model at lower energies we can actually measure.
So it's less about specific models and more like mapping out all the possible tiny deviations from what we know. A giant checklist.
Exactly like a checklist. You take the standard model equations and add every possible extra term allowed by the basic symmetries. These extra terms represent the effects of unknown high-energy stuff.
And the positivity bounds come back in here.
They do, big time. SMEFT generates a huge library of possibilities. Positivity bounds act as a filter on that library.
How so?
They tell us which those possible deviations, which of those EFTs, could actually come from a consistent physical high-energy theory. And just as importantly, they rule out the ones that can't because they'd violate causality or unitarity.
So it helps narrow down the search for new physics, even if we don't know what that physics is yet.
Precisely. It's more driven by data and consistency checks. Look for tiny anomalies in experiments, then use bounds to see which potential explanations are actually viable. It's using fundamental principles to guide the search.
Which brings us back to where we started, causality and unitarity. The talk really hammered home that these are the absolute foundation.
They absolutely are. The whole idea of positivity bounds relies on them. Causality effects don't happen before causes. Unitarity probabilities make sense.
Right.
The bounds are just the mathematical way of enforcing those ideas in our theories. Even when we're dealing with energies in physics we don't fully understand, they stop us from predicting nonsense like negative probabilities or weird ghost particles.
Okay, so wrapping it up, we have these effective field theories, like the standard model and GR, which are great maps but have borders.
Yep, our current best descriptions within limits.
And positivity bounds, based on fundamental causality and unitarity, act as critical checks. They test if these EFTs could realistically connect to some deeper, high-energy theory.
They're consistency checks, ensuring our low-energy picture isn't fundamentally flawed.
We saw how that plays out with tricky ideas like massive gravity, finding that tiny island of possibility, but hinting it must be strongly coupled.
And how it helps filter possibilities in the modern SMFSE approach.
It's really all about using these core principles to constrain what might be out there, beyond our current view.
Exactly. Positivity bounds are a powerful tool, leveraging fundamental truths to navigate the frontiers of physics.
It is genuinely amazing that these, abstract math rules can tell us so much about the fundamental nature of reality. Makes you wonder, what other deep principles are still out there waiting to be found? How else might our understanding shift?
A profound thought. The search definitely continues.
It really does. Well, thanks for digging into that with me. That was fascinating.